Okay, sorry for taking longer to set up. So let's see, everything is okay now. And any question? Hello, hello, hello. Okay, this is working. And so any questions so far? If not, okay, so we will finish our linear algebra today and start talking about some quantum mechanics. Okay, so here is a quick review of linear algebra, and we talk about some matrix properties. There are Hermitian and positive definite, positive semi-definite, unitary, and projective. And those are the definition. Hermitian matrix means A dagger equal to A, and positive definite means that you sandwich it with any vector, then it's positive, and then there is PSD, means that you sandwich with any vector is greater or equal to 0. And unitary matrix means that it is its dagger is its inverse. So A dagger A equal to identity, and projective means that it's square to A. And by projective, we mean Hermitian projective. Okay? And those those operators we all define that they are actually all normal vectors. And I guess here I should do a bit of extra thing. So projective. So P positive semi-definite is P active, we actually mean Hermitian projective. And then because they are all normal matrix, they are unitary diagonalizable, and we can actually characterize their properties by looking at their eigenvectors. So Hermitian means eigenvalues positive, and positive semi-definite means eigenvalues are positive semi-definite, and unitary means eigenvalues has known 1, and projective means eigenvalues are either 0 or 1. Okay. And then we have those 3 matrices, 3 2x2 matrices in computing. They are the X matrix, X poly, Y poly, and Z poly. And once again, X poly is this 0, 1, 1, 0 matrix. Y poly is this 0 minus I 0 matrix. And and Z poly is this 1, 0, 0 minus 1 matrix. And also there is this Hedema matrix, that's 1 over square root 2, 1, 1, 1 minus 1. And because it's important to memorize this matrix, so let's show it once again here. And also you want to know the eigenvectors for Z poly and X poly. So eigenvector for Z poly is this 0 ket, and 1 ket is just this 1, 0 vector, and eigenvectors for X poly is this 1 over square root 2, 1, 1. It's denoted as plus. When we write plus state, it always is this vector. And also there is a minus state, that's 1 over square root 2, 1 minus 1. And then there are Y plus and Y minus that people are less familiar with. And also we like to remember the property of Hedema matrix is basically swap between X and Z, means that you apply it on eigenvector of Z, it becomes eigenvector of X. You apply it on eigenvector of X, it becomes Z, etc. Or you can just sandwich the matrix and get from Z to X or X to Z. Okay. Then there are property of polymatrix, and most interesting one is that the anti-commute. So xy will equal to iz, and xy equal to minus yx, etc. Okay. And then next time we go over this very quickly on tensor product, and let's go through this a bit slower and go to more detail. Okay, so tensor product is a way, mathematically the definition is just a way to multiply any 2 matrices of any dimension. Okay, and it's different from usual matrix multiplication. So usual matrix multiplication, say you have A and B, then those two matrices need to have matching dimension. So you have AB equal matrix A multiply matrix B equal to matrix C. Then usually you have like this is n by r dimension. Sorry, maybe this is n by r, and this is r by n. Then this will be n by n. Okay, but tensor product is quite a crazy definition. It's that you have any n by n A and p by q B, then you can get n by np by nq matrix. And look at this. So you multiply together the row dimension and multiply together the column dimension. And it's a matrix that you place a whole bunch of blocks of B and each multiply with coefficient of A. So those A11, AMI, A1N, etc. Those are coefficient of A, or the elements of A. Okay. And the idea of a tensor product is we want something that satisfies this. Okay, so this property we didn't have explicit proof, but you can prove it yourself by just looking at the elements. The A tensor B times C tensor D will equal to A times C tensor B times D for any matrix A, B, C, D where is. And we have some example of tensor product. So so first we can look at the vectors as matrices, and then we can have two of those column vectors or kth vectors tensor product together. So we have first vector being 1, 2, second vector being 3, 4. Then we can have the second tensor phi ket being this 3, 4 and 3, 4 with the first block multiplying with this 1 and the second block multiplying with this 2. So it's a huge vector that's 3, 4, 6, 8. And then we have more general example where we have two square matrix, and A is this 1, 2, 3, 4, B is this 5, 6, 7, 8, and A tensor B is this 4. 5, 6, 7, 8. We are having 4 blocks here, and each one multiply with 1, 2, 3, 4. Okay, so this is the definition and a very quick idea about tensor product. Okay, and then one obvious thing you can do on tensor product is where you can add together two different vectors or two different matrices that are tensor product of matrices. Okay, so you can have some A tensor B plus some C tensor D. Okay, so for example, if both of them are vectors, so you can have 1, 2, 3, 4 tensor together, adding with this 1, 0, 1, 0 tensor together. Okay, and so if those two are vector, then this will be two huge vector, and you can add together to get a huge vector. Okay. And then we stop here this time. So we analyze the tensor product a little bit more on tensor product for vectors. And tensor product for vectors, we have a whole bunch of notation. A lot of time we do tensor product is tensor product for vectors. So the most standard notation, so you have a vector psi and a vector phi. They can be in different space. And so the tensor product of them together, if you want to write out everything, it's psi, and with this cross and circle thing is tensor. We call it tensor. So psi tensor phi, and then sometimes we will omit the tensor psi and just write the k psi and the k phi. And then you can get more lazy to just write psi comma phi, and people will get even more lazy to write just k psi phi. Okay. And for example, sometimes you can have two qubit tensor together. You have k0 tensor with k0, and it will be written as 0, 0. And in terms of vector, then it will be you write down the vector form. It will be this thing. So will be k0 tensor k0 will be the 0 0 is a 1 0 0 0 vector. Okay. And then we have a bit more notation here. So if psi is from vector space V and phi is from vector space W, then here we also define a tensor product of vector space. So this is actually extra definition, but I guess this definition don't have too much thing. So we also define the vector space V tensor W, and it's just a vector space of spanned by vectors with from some psi from V and phi from W. So this vector space will have also normal basis element with a form I tensor J, where I is a basis from also normal basis element from V, and J is the set of J is a normal. The set of J vectors is also normal basis for this vector space W, and the dimension of this vector space will be A times B, where A is the dimension of V and B is dimension of W. So in this example, we have two-dimensional space, tensor two-dimensional space, then we have a four-dimensional space. Okay? This should be quite intuitive. And yeah, here is the definition that we said about the space V tensor W. It's a space spanned by vector of the form psi tensor phi, and it's a space, so everything inside space is a linear combination of a psi tensor phi. Okay, and then here we go to a bit of a quantum concept. So then we now we can describe the idea about entanglement. Okay, so what is entangles is it's a property of a vector in this space V tensor W. Okay, and okay, so the important thing is that when we define this space, we say the space is spanned by vector over this form. So that means the vector inside the linear combination of this form. But not everything inside this space can be written as this psi tensor phi form. Okay, and here we have just a quick example, which I think probably also in your homework. So you can have the vector 0 tensor 0 plus 1 tensor 1. So 0 tensor 0 is obviously in this tensor form, and 1 tensor 1 is also obviously in this tensor form. And as we say, any linear combination of them, any linear combination of vectors in this tensor form is inside this space V tensor W. Okay? And yeah, so you can add them together, and they are still in this linear space, because linear space, so any linear combination of things inside the space should be also inside the space. And then you can write down the matrix form or vector form of this vector. So z0 tensor 0, as we see, is 1 0 0 0, and 1 tensor 1, it's easy to calculate that, is 0 0 0 1. Okay. And so 1 0 plus 0 0 0 1, you get 1 0 0 1. And then you can just try to do calculation. And just assume you have any two-dimensional vector psi and any two-dimensional vector phi. And when you tensor it together, there will never be this 1 0 0 1 vector. Okay? And when this thing happens, we say the vector is entangled. A vector in this V tensor W space is entangled if it cannot be written as some psi tensor phi, where psi is from vector is from the space V and phi is from the space W. Okay, so this is entanglement, and we'll talk more about entanglement later on when we actually talk about quantum mechanics. But here is a linear algebra definition of entanglement. Okay. And so this is something about tensor product for vectors. Then then let's go back to tensor product itself. So some properties about tensor product for matrices this. So tensor product, and since that it has a name of product here, it satisfies quite a bit of rules for multiplication. Okay, and so those are properties that are satisfied by tensor product. And for example, you can have scalar multiplication on a tensor product, and you will apply in the you will respect the, I guess, associated rule and also commutative. So you have some scalar z on A tensor B, you will be same as you multiply this scalar on A first, or you multiply this scalar on B first, it's the same result. And basically it's easy to see. You just if you go to those element-wise definition, say this thing, then you see that you multiply this thing by a scalar, you just multiply everything by some number, by the same number z, and the same as you multiply this with the number z, or you multiply this with the number z. Okay, so scalar multiplication, and then it also satisfies tensor product also satisfies the distributive rule. So you have A plus B tensor C will be same as A tensor C plus B tensor C, and A tensor B plus C is same as A tensor B plus A tensor C. So from the first three rules, you see that it's a very nice respect the linear property. Okay. And then we have more funny rule on the first one. So the first one is probably a bit less intuitive, and it's kind of I guess it's not just notation, but yeah, just need to remember the rule actually works this way. Okay, so this is what happens when we compose tensor product with dagger. Okay. So if you have A tensor P and apply the dagger operation, which is conjugate transpose, then this thing actually equal to A dagger tensor B dagger, and you need to remember that the order of the tensor product doesn't change here. It is A on first slot, B on second slot, then it's still A dagger on first slot and B dagger on second slot. And this might be unintuitive to you, because if you remember, so usually when you have some matrix operation, say you have A times B dagger, then that thing will equal to B dagger, A dagger. Okay. This is usually what happens when you have a transpose. So also I guess AB transpose will equal to, let's not write it. So AB transpose will equal to B transpose times A transpose. But for tensor product, this doesn't happen. So it's AB here and still AB here. And in particular, so corollary for this is that when you try to tensor product two vectors, so sorry, dagger two vectors, so you want to see what's the dual of some ket vector V and tensor with ket vector W. Then it's actually the broad vector V and tensor with a broad vector W. And here you also need to remember that the order doesn't change. So the dual of this VW ket is the VW broad. It's not WV broad. And yeah, and yeah, so this is different from, as we said, this is different from what you expect from dagger in two matrix. But if you think about tensor product, actually means that you have those slots one by one, then this makes more sense. So then we have this rule that we say we really like tensor product about. So when you multiply matrices of tensor products, then each slot just multiply together. So you have A tensor B times C tensor D, then you have AC, A times C, tensor B times D. So the matrix multiplication respect the slot location of your tensor product. Okay, and so this is kind of why we this VW dagger equal to also VW, because let's give a little bit. So if you have a whole bunch of things, whole bunch of tensor multiplying together, so you have A broad tensor B broad multiplying with A tensor B, then multiply with C tensor D, then it's every so then it will be all the first slot calculate the first together and all the second slot calculate together. So you will have A broad times A times C here, then B on the first slot, then tensor on the second slot will be B times B cat times B matrix times B broad times B matrix times D cat. Okay. And so you can calculate the first slot, then tensor the second slot. And in this example, you also see that you can omit a tensor because this is a number, this is also a number. So you just have two numbers multiplying together, and it gets a number. Okay, so yeah, hopefully this makes sense now. So you have two vector and two vector tensor together. You take it as a dual, then it's then the ordering of the two vectors doesn't change. Okay. And then lastly, we have this property of tensor product that just says that it's associative. So you can have two matrices tensor together, and tensor a certain matrix will be same as you tensor these two matrices first, and then tensor the first matrix. Okay. And yeah, I think this is the last slide. Here are some calculation examples. So you have V and W square, V tensor W, and you want to calculate its norm, and then it's inner product with itself. So it's the dual of it multiplying with itself. And then here we see that the dual of it is the order doesn't change, so you just flip V cat to V bra and W cat to W bra. Okay, then you have this V bra tensor W bra and multiplying with V cat tensor W cat. And once again we use this fifth rule, where each slot is multiplying together. Then we have V bra times V cat, and then tensor W bra times W cat. And as in the second example, this is just two number multiplying tensor, two number tensor together. But we have a 1 by 1 matrix, tensor 1 by 1 matrix is still a 1 by 1 matrix. So we just V inner product with self times W inner product with self, and we see that it's a non-square of V times non-square of W. Okay. And yeah, so so this is also a nice property you can derive from tensor product, and you see that this dual notation makes that we have a nice definition of the length of this V tensor, length of the V cat tensor W cat. So length is just the length of V times the length of W. Okay, so that's the last page of this slide. Any questions so far? If not, then we can finish our linear algebra now and go to quantum mechanics. Okay, let's try to open quantum mechanics. Quantum mechanics. So this is the first set of slides on quantum mechanics. Okay, so now we go to introduction of quantum mechanics, and and this is our scope of PTT. Scope of this slide is about chapter 2.2 and chapter 2.3 of the Nielsen Tron textbook. Okay, so a bit of a reminder of quantum mechanics we talk about is we say that this is our overview for quantum mechanics. So there is some quantum world, and there are some feature division between quantum worlds, quantum stuff, and the classical observer we are familiar with. And we say that to get information out of the quantum stuff, what you need to do is measurement. Okay, and okay, so to get information out of a quantum system, we need to do measurement, and this is very different from classical mechanics in how information is handled. Okay, and so the different part is that the measurement will disturb or will collapse quantum state, and will output a result with probability. And whereas in classical mechanics, you usually assume measurement doesn't change your state. You just your system is have upspin, then you measure it is in upspin, etc. Okay. And then we also hint a little bit that the quantum measurement is more complicated than classical measurement, and I think we should be able to see this today. Okay. And then quantum measurement is even more complicated than classically measuring a random variable, and we'll see it today. Okay. And we start with quantum postulates. Okay. And yeah, this is how we assume quantum mechanics work. And so there are 1, 2, 3, 4. And the first one is that any quantum state is a unit vector in a complex. It's a unit vector in a complex vector space. Okay, complex linear space, and we call it maybe H. Okay, and so for example, we can have our complex vector space being a three-dimensional complex vector space, and our vector can be, well, it's a three-dimensional vector, then you can write it out with coefficient. It will be some A00 cat plus A11 cat plus A22 cat. And we say it's a unit vector, means that the length of a vector being 1. So it's A0 squared plus A1 squared plus A2 squared should equal to 1. Okay. And then so this is kind of we already know and expect for quantum mechanics. Then the second thing is something that we didn't talk about before, but now we can say more clearly. Now we know linear algebra is that when we change a quantum state, get changed by a unitary matrix. And why we change it with unitary matrix, now we know is because unitary matrix doesn't change the length of your vector. Okay. So you start with a unit vector and you want your state to stay as a unit vector. So that's why you change it with a unitary matrix. Okay, so when you do some operation on your system and something will happen, and the something happen is always a unitary matrix. And so I guess as an example of computation, then maybe your qubit start in the state 0. Then you apply a gate. That gate will be a unitary matrix, and the state of your quantum computer will change to a different state. And for example, you can change from this 0 cat and apply a unitary matrix which is Hadamard, and it will become this 1 cat. And in terms of matrix calculation, we have a handwritten here. So handwriting here. So 0 cat is this 1, 0 vector. And you get rotated by this Hadamard matrix, which is 1 square root 1, 1, 1, 1. And you multiplying it on this 1, 0 vector, then it becomes this 1 square root 2, 1, 1 vector, which is also the plus vector. Okay, and yeah, so so your quantum state get changed by this unitary matrix. Okay. I guess this is a part that's different from probability, because probability you go by it's called Bayes' rule, but in quantum mechanics you are changed by unitary matrices. Okay. And then third one, we say that when we do we can do computational basis measurement quantum system. This is the measurement we talk about. And you can do computational basis measurement on your quantum state, and you will collapse your quantum state into the computational basis state. So computational basis state, we assume that in each system we just so now go to a bit of physics. So each system we assume there is some natural direction that you set it as computational basis. That is 0, 1, 2 to n-1. Okay. Anyway, when you do computational basis measurement, then your quantum state will collapse into different I. So the I can be any I from 0 to n-1, and the probability of your state going to I is alpha I squared, alpha I absolute value squared, and then this is why we want those alpha I absolute value squared sum to 1, because you want the measurement probability sum to 1. And the observer will also know that when you do measurement, you will also learn which I the state turn into. Okay. And then also there's this fourth rule about tensor product. So let's say you have a multiple quantum system of space, so space h1, h2 to hn, and we assume so we have a whole bunch of quantum system and they interact some way. But before we talking about later interaction, we talk about their state. So we have a state in each system. Then the state of the composite system is in this huge Hilbert space, which is the tensor product of each Hilbert space. Okay, and let's see if I can do this. Never mind. Yeah, that's too complicated. Sorry. And yeah, so this is kind of why we talk about tensor product of spaces, and yeah, so when you have a multiple systems interact together, then the state of composite system is actually in this tensor product of spaces. And this is also kind of where we talk about entanglement here. So you can see entanglement is a weird thing here. So you can have each system is in some state, then the total state of the system will be the tensor product of all the K's. So say you can have each system was in Kt1 and Kt2 and etc. all the way to Kn. And then if each system is in those K state, then the state of the whole system will be just those in tensor together, right? Will be this tensor all the way. Okay? But we also talk about there's entanglement. So maybe you start with every system separate and you have this state. But when you have interaction on this system, then you should apply a unitary light on this whole linear space. Then you can start getting entangled state. And the entangled state, as we say by definition, is not the composition of each individual state. Okay. And yeah, then that's some weird quantum phenomena we'll investigate more. Okay. And also note that the dimension of the Hilbert space is really large. Say each space, if it's just the smallest possible one, is just 2 dimension each one, then the dimension of n of them together will be 2 to the n. Okay. And just think about this 2 to n dimensional space. There are a lot of information you need to use to describe even a vector in 2 to the n dimensional space. And this is one of the weird quantum phenomena that we'll investigate. Okay. And so those are simple quantum postulates. But we said that today we want to talk about focus on measurement. Okay. And so actually there are a lot of measurements that you can do. Okay. In this simple quantum postulate, we just talk about computational basis measurement. So I say we do measurement, then your quantum state collapses into computational basis state. So this is whatever I. And you might ask, why is there a special direction for every Hilbert space? And so the linear space, you think about it, is quite symmetric in any direction. You can pick many different orthogonal bases. And indeed, you can also do measurement in any other basis. Okay? And so when people talk about measurement in the literature, there are actually many different things. Okay? And so this is actually from top to bottom are generalization of a measurement scheme. Okay, so the most basic measurement you can do on quantum system is what we just talked about. It's the computational basis measurement. Okay, and then just as we said, computational basis is a spatial basis, and where can you only do a measurement in that basis? And the answer is that actually you can do measurement in any orthogonal basis. and you will project your vector, your quantum state into that orthonormal basis. Okay, and then there is also a different thing. A different way that people talking about measurement is measuring a Hermitian operator, and this one is more physics oriented. So if you learn quantum mechanics from physics department, then a lot of time then most likely you are talking about this measuring Hermitian operator. Okay, and then lastly, in this course, we will talk about generalized measurement, and this is a measurement that is taught in the book, and we also have a formulation later. Okay, and yeah, we see that we can just have a set of operators, and then we just say a set of operator will define a generalized measurement. Okay, and yeah, so let's see those different measurements. So we'll already see computational basis measurement, and we said before that the computational basis measurement looks really like just measurement looks just like a probability distribution. And it just gives you this alpha I squared. Then why don't you just define this as a probability and just say we have a probability mixture, and we look at the thing, we get something with probability. And the orthonormal basis measurement kind of answer this, because you can also measure a quantum state in different directions. So you can actually pick any orthonormal basis for your Hilbert space and do a measurement with respect to that basis. Okay, so you have any quantum state psi in some space H and orthonormal basis V of that space H, then you can measure it, and it's a lot like computational basis measurement. So you will get a random VI as outcome, and the probability is just a coefficient of your psi on VI. So probability of getting I is a coefficient of psi on VI, which is the inner product of VI and psi squared. Okay, and for example, let's just see example here. You have psi equal to A0 plus B1, and you measure in this 0, 1 basis, which is just a computational basis. And so probability of getting 0 is 0 inner product with psi absolute value squared, which is just A absolute value squared. And the post-measurement state, when you do a measurement and get this 0 outcome, your state is 0. And then similarly, you can get one outcome with some probability, and the probability is this coefficient B here, because you take a one inner product with psi, you get this B. Okay, and yeah, then let's change to a different basis. So we have this 0, 1 basis. We can also measure in plus minus basis. Okay, and remember, plus and minus are the eigenvectors of x poly, and they are those two vectors. Plus is 1 over square root 2 1 1, minus is 1 over square root 2 1 minus 1. Okay, and now let's try to do the same thing. Okay, so you measure in plus minus basis, then you will get the plus state as a post measurement outcome with some probability, and the minus state as a post measurement outcome with some probability. And the probability of plus is the inner product with psi squared. And you take this thing, inner product with this thing, and this should be 1 over square root 2 from here. And because you have 1 1 here, this is just A plus B. Okay, so 1 over square root 2 A plus B squared, and it's 1 over 2, then A plus B absolute value squared. And then similarly, the probability of getting the minus outcome state is what absolute value square of this minus vector inner product with this vector. And now you have a minus here, so your B will get a minus sign. So you have 1 over root 2 absolute value A minus B squared. Okay, and yeah, and here we have a little side note. And then what we say we can do all orthonormal is that in terms of what the computer can do, I guess in terms of what the computation can do with the postulate, so that's back to that line is actually referred to here. So having so stating that we can only do computational basis measurement is same as saying that we can do any orthonormal basis measurement, because you can just do a changeable basis with this second thing here, right? Because if you want to do a computational basis measurement, if you want to do any orthonormal basis measurement, then you can just rotate your state with unitary matrix first, then do computational basis measurement. Okay, and so for example, I guess maybe it's easier to say example. If we want to do to do this plus minus measurement, we can do, I guess here is a good time to ask question. Anyone to answer what the unitary should we apply on our vector? Anyone want to answer? If we can just apply some unitary on our state, then we will do computational measurement before we do computational basis measurement. Okay, so what's the unitary connecting the plus minus basis and the 0, 1 basis? Okay, and the unitary is the Hedman unitary. Okay, so I guess you can check yourself that if we apply Hedman on our side first, then do computational basis measurement, the same as you doing this plus minus basis measurement. So if you do this first, then do computational basis, then I guess it's a little different. So you will get two computational basis state, but the probability you will get those two states with these two probability, and then you want to change those two states back to plus minus state, you apply another Hedman. Okay, and so this is really just a changeable basis. So because you can do in quantum computation, we can do unitary operation to change to switch in between any orthonormal basis. So really you can do measurement in any basis by just doing computational basis measurement conjugated by unitary matrices. Okay. And later on we'll see, you can hopefully already get a feel about this is very different from classical, and here is more I guess here is a more detailed calculation of what we say. Okay, and in terms of computation power, orthonormal basis measurement is the same, because we can do changeable basis, and so if we want to make basis, and we can do Hedman gate first, and then we will get psi to Hedman psi equal to this psi prime, and now if we measure psi prime in 0, 1 basis, we are interproducting this psi prime with 0 and 1. And but we know so 0 bra times Hedman is actually equal to plus bra, because I guess here this is okay. So I should first erase this thing. What do I erase later? Sorry. Okay, and this thing, I guess we don't have that exactly, but this thing is the dual of Hedman plus 0, and we know this thing because not Hedman plus Hedman dagger, and we know Hedman dagger equal to Hedman, so this is equal to Hedman 0. Okay, so this is a bit of calculation here. Okay, and we know its dual is Hedman dagger 0, and this is equal to headma 0, and this is equal to plus, and so this is plus inner product with 5 squared, and it's exactly this p plus probability we calculated before. Okay, and also this side product measure with measure this side product getting the probability of it getting one outcome. Similarly, is one inner product with headma with psi, and it's this minus bra inner product with psi, and it's similarly is this p minus probability. And then, as we said, post measurement outcome state here is 0, and you can apply headma on it, and then it will become plus. So you change it back from 0 minus 0 1 basis to plus minus basis, and the post measurement outcome here is minus, and you can apply a headma on it, and get back to, oh sorry, this is 1, sorry. The post measurement outcome here is 1, and you apply headma on it, and you get minus. Okay, and I guess we don't have time to finish all measurement, so I will flash the next one. So next, and maybe stop early. Okay, so the next one we have measurement by a Hermitian operator, and here we use the fact that the any Hermitian matrix is unitarily diagonalizable. So you can write it in this way: it's the sum of some real eigenvalue and then projectors onto its eigenvectors. So A equal to some I lambda I, then this vi, which vi are just eigenvectors, and they should be also normal. Okay, and really a measurement by Hermitian operator, it can be looked as a generalization of measuring against the orthogonal basis, because we already got the orthogonal basis of those eigenvectors here. Okay, and so measuring a Hermitian operator is basically just measuring this orthogonal basis, but where the outcome you just label as eigenvectors. Okay, eigenvectors lambda I. And this thing has a physics motivation, because usually we think this Hermitian operator is some physical quantity. So very many, maybe the position of your particle, momentum of your particle, or spin of your particle, etc. And so the lambda I will just correspond to the measured physical quantity. That's why you have quite an arbitrary lambda I here. Okay? And lambda I need to be a real value. So maybe lambda I equal to 1, you say your particle is at this position 1 meter, something like that. Okay? And lambda I is -2, then your particle is located at position -2 meter, something like this. And so this is very similar to, mathematically, this is very similar to orthogonal basis measurement. You just diagonalize your matrix and get the orthogonal basis, but there are two different things. Okay? And the first is that there is a physics connection, and the outcome we just label them by the eigenvalues lambda I. And then the second thing is the degeneracy we talked about, and we don't have time to go to detail. But sometimes there are many lambda I that has the same eigenvalue, and then in that case, the measurement is actually a bit different. And yeah, we'll see about the details about degeneracy next time. And for now, let's see that we have a measurement against orthogonal basis, and we now know that we can measure our quantum state in different bases. And this is a big part of why quantum information is different from classical information. Okay, so yeah, see you Thursday, and we'll talk more about